Now we're going to do lab number 5, investigation 2, where we'll actually determine force and mass units and show the relationships there. Okay, so in investigation 2, so far what we've done is we've measured in standard units of pull exerted by the force sensor, or on the force sensor, calibrated in newtons. So where does the unit of the newton come from? By contrast, we've used our own private unit of measure for mass called the cart mass. And if another group were to use a large wooden cart in their force and mass experiments, and another group use a small aluminum cart with smaller mass, they'd have different values of mass. So we've got to have some kind of standard unit of mass, because we'll see different accelerations if we have one cart mass being pulled by 1 newton of force. So let's go ahead and establish standards. Now, I've talked about standards already in class, and on page 116 there's a little bit of a discussion. Our fundamental standards are the unit of length, which is the meter, the unit of time, which is the second, and the unit of mass, which is the kilogram. So our standard unit of force is going to be the newton. And I've already mentioned in class that it's defined as the force which causes a 1 kilogram mass, or excuse me, I've said that a newton is equivalent to 1 kilogram multiplied meter per second squared. Now, through the experiments, I can give it a physical meaning, which is 1 newton is the force required to accelerate 1 kilogram of mass by 1 meter per second squared. So let's go ahead and see if that ratio actually goes into play. Okay, there's going to be a lot of uncertainty as we go along, especially as we get into bigger and bigger units of force. So let's see where we go from there. Let's start with activity 2-1. Okay, in investigation 1 of this lab, we've already measured the force applied to a cart and the accelerations of the cart with masses equal to 1.5, 1, 2, 2.5, and 3 cart masses. Now the question is, so let's go back to the table, which I already have displayed on the computer, and let's copy the values, we put them in. What we need to do next, for each row, we calculate the ratio of the force to acceleration. So I'm going to go ahead and create a new calculation. And the calculation is going to be, calculation is going to be average force divided, I believe it's average force divided by acceleration. So average force divided by acceleration. And that doesn't quite give me, let me go ahead and use my calculator function here, and we can do this a little better. Okay, we're going to go ahead and call this, or just call this ratio. And ratio is going to be equal to the average force. So is going to be average force divided by the mean acceleration. And the units should be in kilograms. Actually, we're going to use it in cart masses, so we're just going to call this carts. See if this is going to be the same units. Okay, so what did we end up getting? Well, not quite. Not quite what we expected. We had a 1-to-1 ratio of average force to mean acceleration. Okay, so that was almost 1. Then we had a mean acceleration, so this is F, this ratio is force divided by acceleration. And when I mentioned that there was going to be uncertainty, it certainly is. 0.5, 0.69, 0.1, 1.15, and so on down the line. Now, here comes an interesting thing, though. We can actually do something about this. This ratio of carts, according to the discussions, the numbers you calculated should be the masses of the objects in kilograms. Okay? Well, turns out that the cart masses in kilograms is, in the first case, 0.35. Then we go to, let me see, I've got those listed already, 0.35. Then it's 0.525. then 0.750, then 0.875, and then 1.05. Okay, now let's do a comparison. 0.5 to 0.35, 0.69 to 0.525, 1 to 0.75, 1.15 to 0.875, 1.35 to 1.05. It looks like there's a consistent error. It's a relatively consistent error. Let's actually work that out. Okay? So the first thing we get is from the ratio. We get 0.50 is from the ratio. From the cart masses, from the measured cart mass, we have 0.35. So that means the error is going to be 0.15 kilograms. So there's a 150 kilogram difference between the two. Now let's take a look at the second one. We have 0.69 and we have 0.525. So 69 minus 5.3 gives me 6.1, so it's about 100.16 kilograms. Then in the second case we have a 250. We have a ratio of 1.0 to 0.75. So we have a 0.25 kilogram error. Then we have 1.15 from the ratio and 0.875. So that looks like a difference of just around 0.22 kilograms. So we're going to have an error. The error seems somewhat consistent. The error seems to build as we increase the cart masses. What that means is there's probably another force, there may be other forces involved in our ratio here. So that's where our uncertainty is going to come into play. Okay, so the question is, are your inertial masses reasonably consistent with your masses measured with the scale or balance? Well, here's one way we can check it internally. Okay, so here's our mass 100. Okay, right here is our mass of 100. When we doubled, or when we halved the cart masses, the ratio halved. That makes sense. When we went from our base, so here's our base, 0.5, we double that, we get to 1. We triple that, our 3 cart masses, we ended up getting 1.35, so there's a little bit of an error there. So what I'm trying to get at is, it is reasonable. We are starting to see something reasonable here, that the ratio seems to be consistent. It's a lot of uncertainty involved here because of other factors that come into play. This cable here is going to impart a force. Frictional forces in the wheels are going to impart a force. So that's going to make some changes there. And of course, there's another reason why, which is namely the mass at the end is going to impart a force as well. It's going to change things around. Let's go ahead and go to activity 2-2. And in activity 2-2, the question is, does a force of 1 Newton applied to a 1 kilogram mass really cause an acceleration of 1 meter per second squared? So let's go ahead and set this up to get 1 Newton of force. So I'm going to go ahead and set this up and see where we go from there. Got it set up now? What I have is the cart now has a mass of 1 kilogram. That is to say, the 350 grams of the cart plus an additional 650 grams of additional mass. This gives us a mass of 1 kilogram for the cart. To make the force, I've added a total of 100 grams hanging over the side. We'll do the experiment and see if this actually is the case. So the mass of the cart on page 119, mass of the cart is 1 kilogram. Let's go ahead and zero the sensor out. Pull it way back. Now this is going to be perfectly honest, a somewhat violent reaction, which is why I've got the bumper out. So let's see what happens. I'm almost afraid to let it go. There's the collision. Obviously, our force sensor didn't work. Our acceleration is too slow. Let's go ahead and repeat the experiment. We're going to zero the force sensor again. Zero the force sensor again. And let's give it another go. Like I said, it was a somewhat violent because the masses fall off and stuff goes flying everywhere. But let's take a look at what the acceleration is. If we look on the slope, we see the acceleration is 0.8 meters per second squared. Our mean is 0.93 newtons. So we don't have enough force yet. So let's go ahead with, let's see, I've got 100 newtons over there added on. So let's add on another 10 grams and see if that increases our force up to 1 newton of force. Again, 150 grams. I believe it. Yeah, 150 grams added on to that. Sorry, total of 650 grams to the 350 grams of the cart. Okay, we've got it all set up. Zero the sensor again. And let's go ahead and do the experiment. Okay, now what do we see? We see we have achieved 1 newton of force. 1 newton of applied force, but it has accelerated the cart to only 0.91 meters per second squared. If I'm going to get this accelerated even more, so mass of the cart in kilograms was 1 kilogram. The average applied force, we can see there, is 0.99 newtons. The average acceleration is 0.91 meters per second squared. And the hanging mass turned out to be 115 grams, 0.115 grams. Now, how close is your result to the expected value of the acceleration, 1 meter per second squared? And it's close. It's certainly consistent that if we add force, we should get greater acceleration. But what are the uncertainties? And I'll tell you what the biggest uncertainty is, and I'll show you how it works with this diagram here. You see, the issue is that while we look at the cart, which has a 1 kilogram mass, it is certainly being accelerated, A, in that direction. But the cart is being held by a string, which is being attached to a mass, M. This mass is being pulled down by the force of gravity. I'll talk more about coupled objects in a moment, but let me go ahead and walk through a free body diagram real quick. Okay, so my free body diagram of the cart is I have the mass of the cart, the weight of the cart pulling downward, W pulling downward. I have a normal force pushing up, which is not going to affect the acceleration, so we can go ahead and get rid of that. But I do have the cart being accelerated by a tension force going in that direction. On this side, we have a mass pulling downward, so I'll call this W2. And then we have a tension force pulling upward, because the tension of the string pulling up on that. And this whole thing, this is going to be accelerated with the same acceleration. So now let's do a little bit of math. This free body diagram gives us an equation. Normal and weight cancel out, so really it's just the tension causes the mass of the cart, I'll call mass 1, to have an acceleration. For this one right here, tension and weight are going to add together. And so I can write that since the weight is pulling in the same direction as the acceleration, I'm going to call weight positive. I'm going to subtract the tension, and that's going to be equal to mass 2 times its acceleration. Okay. So far, so good. Let's finish this up. That means that when we put the equations together, the weight pulling downward minus the tension which is going to be equal to mass 1 times the acceleration equals mass 2 times the acceleration. And here's the fundamental thing. What's causing the mass to accelerate? It's this weight. But the weight is not just accelerating the cart. The weight has to accelerate both mass 1 and mass 2. And that's the big difference. That's the big difference right there. So if we have 1 kilogram, so if the net force is 1 kilogram, or if the force that's pulling downward is 1 kilogram, we're not 1 kilogram, excuse me, it's pulling down as 1 Newton. We're not accelerating 1 kilogram of mass. We're actually accelerating 1.1 kilogram of mass. And so we see the acceleration is going to be slightly below 1 meter per second squared. Okay. The only way to really tell is if I took a cart and grabbed it and I applied 1 Newton of force in this direction. So I'm only accelerating the cart with that particular force. So that's the reason why we have that uncertainty in question 2.3. In question 2.4, a force of 0.54 newtons is applied to an object. The object is observed to accelerate with 3 meters per second squared. The friction is so small it can be ignored. What's the mass of the object in kilograms? Just do the division. Force divided by acceleration will give us the mass. Question 2.5. An object of a mass 39 kilograms is observed to accelerate with an acceleration of 3 meters per second squared. What is the force applied? Now we apply Newton's second law again. F equals ma. We know the mass. We know the acceleration, so the applied force is the product of the two. Okay? So anyway, go ahead and answer the questions in activity 2-3. This finishes up investigation 2, and it also finishes up lab number 5. Again, if you've got any questions, please get in touch with me. This has been a very interesting examination. We have only one more lab left to examine forces, and that's going to be lab number 6, when we'll specifically be looking into the effects of gravity on moving bodies. Thank you very much.